Well, good morning once again. Adam Eldridge here from West Valley High School of Yakima, part of the Central Cornerstone program as well. Lecture today on Math 154, Section 6.3 in the current edition of the Central Washington University book, dealing with right triangle trig. So let's look at our objectives for today. We're going to talk about solving right triangles. That is, given an angle on one side, can we find other sides within that triangle? We're going to apply what we know about trigonometry to solve some real-world problems. We're also going to look at how we can calculate the area of any triangle, calculate the area then of any regular polygon by breaking it down into triangles, and solving real-world problems involving angles of elevation and angles of depression. Again, we're primarily dealing with right triangles today. Later on, in subsequent lessons, you will learn a little bit more about using law of cosines and law of sines to solve things that are non-right triangles. So first thing I want to look at is to again remind us about using trig to find missing lengths of sides. And as a reminder to many of you, I'll write SOHCAHTOA across the top here. Remember that in a right triangle, the sine is the opposite over the hypotenuse. Cosine relates the adjacent side to the hypotenuse, and tangent is the opposite side to the adjacent. So right now on your paper, I want you to please calculate side length represented by A and the side length represented by B. And if it's not shown up very clearly here, this is a 23-degree angle right here, and our hypotenuse is 30. And please calculate A and B to the nearest tenth of a degree. One key thing to remember when solving trig equations is to use your pictures. Label them, draw on them so that you can adequately see where the relationships are. Trigonometry to me is a very, very, very visual aspect of area of mathematics. So we know that the sine of the 23-degree angle is a relationship between the side opposite that angle, which in this case would be A, and the hypotenuse, which in this case is 30. So sine of the angle that we know is equal to A, which we don't know, divided by 30. So if I want to find out what A is, I would multiply both sides of my equation by 30. So I'm going to take 30 times the sine of 23. And before we calculate that, actually I've got that here, we should have gotten 11.7. And the cosine of 23 so if we're looking at, again, relative to the 23-degree angle, cosine would relate our adjacent side to the hypotenuse. So that's B over 30. So B is equal to 30 times the cosine of 23. Let me remind you once again that one of the most common mistakes my students make is they'll have their calculator in radian mode instead of degree mode. So if you didn't get an answer like 11.7 on this first one, or on the second one here for B, if you didn't get 27.6, then you should check to see that you're in degree mode. That'd be the first place that I would look. It's always good to check for reasonableness. One of the nice things about trig is we've got a picture that we can relate to it, and we can pull back in information from our days in geometry. If this side here is 11.7 and this one is 27.6, you have to ask yourself if those are reasonable answers for the situation. What do I mean by reasonableness? Well, one thing to note is that in a triangle, the hypotenuse should always be the longest side. So if either of these other two answers were bigger than 30, we would have a problem. Another thing to note here is the sum of two sides of a triangle needs to be longer than the third side as well. So if I had 11.7 and I got 11 for this one as well, the sum there would only be 22.7, which is not larger than 30. I have a problem. So in this case, 11.7 plus 27.6 is greater than 30, so it makes sense that we have a triangle here. So two things to check for reasonableness are one, that your largest sides correspond to your largest angles, and that your side lengths correspond in such a way that you have a triangle, that the sum of the smallest two sides of the triangle is larger than the third side. So, an applied problem. This is one of those canned geometry problems that are a trigonometry problem that shows up in almost every Algebra 2 and pre-calculus textbook. A 15-foot ladder leans against the side of a building, forming a 70-degree, lost my degree sign, angle with the horizontal. How far from the base of the building is the base of the ladder, and how high up the wall will the ladder reach? Again, students in my class, first thing I'm looking for is a picture. Could you do this one without a picture? Probably, but you're less likely to make a mistake if you can visualize what's going on here. So we'll start by drawing a building, and we'll lean a ladder up against that building. So the horizontal in this case is the ground. We've got a ladder, and we've got a building. And in this course, we're going to assume that buildings are built perpendicular to the ground. So we do have a right angle here. Not all buildings are that way, especially if I'm building them, but we're going to hope that our building is making a right angle with the ground. So let's take the information from the problem and put it on our picture. A 15-foot ladder. Well, that 15-foot ladder is right here. Forms a 70-degree angle with the horizontal. That means I've got a 70-degree angle here. How far from the base of the building is the base of the ladder? That's this distance from here to here. I'm going to represent that with x. And how high up the wall will the ladder reach? That's this distance here, which I will relate with y. From the picture, we see we have a right triangle where we know the hypotenuse, we know one of the acute angles, we also would know the other one would be 20 degrees, and we want to know both the adjacent and the opposite side relative to that 70-degree angle. So, sine of 70 degrees is equal to y over 15, and cosine of 70 is equal to x over 15. Key things to remember here. First of all, draw yourself a picture. Figure out what sides you know something about and what sides you want to know something about. I knew the hypotenuse. I wanted to know both the opposite and the adjacent. So opposite with hypotenuse was sine. Adjacent with hypotenuse was cosine. So drawing a picture and thinking about what do I know and what do I want to know will help you in setting up these problems. So y, which represents the distance up the wall that the ladder would reach, is 15 times the sine of 70. And x, which represents the distance from the base of the ladder to the base of the wall, would be 15 times the cosine of 70 degrees, which is approximately 5.1, x is 5.1 feet, and our height was 14.1 feet. So always be sure that you're answering the question that is being asked. In this particular problem, they were asking for this distance and this distance. So I can go back and label these 14.1 feet and 5.1 feet. Our next concept here is finding the area of a triangle. Now back in elementary school, you were first introduced to the concept of area. And one of the figures you probably dealt with at that time was a triangle. And from your previous mathematics experience, you know that the area of a triangle is 1/2 base times height. One important thing to remember here, though, is that your height has to be perpendicular to the base that you're dealing with. So we had to know a relationship where the base and the height were in fact perpendicular. But like we see in this triangle here, our triangle ABC, we don't know that we have any of these angles as a right angle. So we don't know that we have a perpendicular relationship between any one side and one of the other sides of the triangle. So what we would do in that case is we would draw in our altitude, and we would want to know what that altitude is. And we would take 1/2 that altitude times the base that it is perpendicular to. Now, if we were doing a lot of problems finding areas of triangles, we could use trigonometry to help us figure out what that altitude is. Again, back in elementary school, they would just give you that height of the triangle. But at this level, we can find that height using trig. In this picture, I have theta. And this altitude that is drawn in here with the h is perpendicular to side B. I want to know what h is. So I can think about what relationship would equate theta with h. Well, I also know side A is part of that smaller right triangle. So I can see that sine of theta is equal to h over A. I also know that the area of a triangle is 1/2 the base, and I've represented that base here with B, times height. Well, we can do a substitution here, where I multiply both sides of this equation by A, and h is equal to A times the sine of theta. So I can substitute this h in here, and I get 1/2 B h times the sine of theta. Sorry, that's an A, not an H. Let me just rewrite that here. 1/2 B times A sine of theta. And so in your textbook, you're most likely going to see an area formula for a triangle being 1/2 AB times the sine of the angle that is between those two sides. In any triangle, if you know two sides, and the two sides, in this case A and B, and the angle between them, in this case angle C, then the area of that triangle is 1/2 the product of the two sides times the sine of the angle between them. Pretty useful tool. We can use it no matter what the triangle looks like, as long as we have two sides and the angle between them. So let's apply that to finding the area of a regular polygon. A couple things to remember. Again, there's a lot of geometry involved in trigonometry. So regular. Well, regular means that it's equiangular and equilateral. That's one of the key things to remember. A hexagon, you remember that hexagon means that it is six-sided. So what we have in this picture is we have a circle where a hexagon, a regular hexagon, has been inscribed inside of the circle. One of the useful things to do is to draw a triangle, and break up this hexagon into a bunch of triangles. What we have here is we can break the hexagon into 6 congruent triangles. Now each of these triangles is congruent. Each of them is also isosceles because each side of these triangles represents the radius of the circle within which it's inscribed. So we need to know what this angle is so that we can find the area of one of these triangles. Well, the hexagon's kind of convenient here, but we'll go through the process much like we would if it wasn't a hexagon. If I separate this triangle out, I know that this is 5 and this is 5, and I need to know what this angle is. From your geometry experience, you'll know that in a regular figure like this, if we take 360 divided by the number of sides of our polygon, that will tell us the measure of that central angle. So this is a 60-degree angle, That means that in this particular triangle, it is equilateral. But if we were working with a pentagon, for instance, if we were working with a pentagon, we would take that 360 and divide it by 5 and get a 72-degree angle. So in a pentagon, we wouldn't get this nice equilateral relationship. We would still have an isosceles triangle, but we wouldn't have an equilateral one. I chose an equilateral on this one just because of we can see an exact value of it. And so let's calculate the area of this one triangle. In the previous slide, we said that the area is equal to 1/2 product of two sides, 5 and 5, times the sine of the angle between them. So what I'm looking at is the area of one of these triangles that I'm then going to multiply that quantity by 6. So this is 12.5 times the sine of 60. From our previous discussions, we know that in a 30, 60, 90 triangle, this is a 60-degree angle. This is root 3 compared to 2 compared to 1. We know that the sine of 60 degrees is root 3 over 2. So we know the area of one of these is 12.5 times the square root of 3 over 2 centimeters squared. And the area, and that's a decimal point, not a multiplication, and the area of the entire hexagon here would be 6 times 12.5 times the root 3 over 2, which is 37.5 times the square root of 3, and our units there would be centimeters squared. So big idea here, if we're given a regular polygon, we need to break down that regular polygon into triangles. We can find the area of one of those triangles using the formula we developed on the previous slide, and then multiply it by the number of triangles that are formed. And again, because this is a regular figure, each of these triangles will be congruent. Last big concept for today is looking at the angle of elevation and the angle of depression. And what are definitions here? An angle of elevation is the angle through which the eye moves up from the horizontal to look at something above. So if I'm standing here, here is the horizontal. And if I see a bird, mad artistic skills that I have, the angle of elevation is represented by how much above the horizon my sight line is to where the object is that I am looking at. So again, this angle of elevation is formed with the horizontal and the line of sight from my eyes to the figure that I am looking at. Now in most trigonometry textbooks, the height my eyes are above the ground is negligible. Sometimes you may say that a person's eyes are 5 feet above the ground. Let me switch pens here. 5 feet above the ground. But generally, if you see an angle of elevation problem in a textbook, unless it specifies that you're taking it from a certain distance above the ground, we assume that the angle of elevation is given from ground level. So when we do some of these applied problems, we typically say that it's with the horizontal being at the ground if we're talking about a person looking up at a figure, unless the height of their eyes is given. So, angle of depression, let me back up. Angle of depression is if we're looking down at something, it's that angle. So if we are looking from So if I'm standing on top of a building, and I'm looking down at something below, here's the horizontal. The angle of depression is formed from the horizontal to my line of sight going down to the object. So angle of elevation is when I'm looking at something, it's the relationship above the horizontal, and angle of depression is that distance below the horizontal. One thing to note, if my angle of elevation to this bird was 15 degrees, from the bird's perspective, the angle of depression down to me is also 15 degrees. What we have here is this is a horizontal line, those two lines are perpendicular, cut by two parallel lines cut by a transversal. We see that these angles are alternate interior angles that are going to be the same. So it's a matter of reference point. The angle of depression from the bird to me is the same as the angle of elevation from me to the bird. So, applied problem, the angle of depression from the top of a cliff 170 feet above the surface of the water to a sailboat is 15 degrees. Find the distance from the base of the cliff to the boat. No pictures given, so I would always start by drawing a picture to represent the situation that we're given. So we know we have a cliff, and from the top of a cliff down to a boat in the water. So here's our water, here's our boat. We know that the angle of depression is 15 degrees. And we know that the cliff is 170 feet above the surface of the water, and we are looking for the distance from the boat to the cliff. Again, it's not stated in the problem, but in most trig textbooks, unless otherwise stated, we're assuming that buildings are perpendicular, cliffs are perpendicular, unless an angle measure is given otherwise. You will see those types of problems when you look at law of sines and cosines later down the road. But for this problem, we're dealing with a right triangle. So my angle of depression here is 15. That means this angle here is also 15 degrees. If we wanted to, we could also look at it from the perspective of this angle right here, which is going to be 75 degrees. It's complement. 15 and 75 are complementary angles. So we can set up an equation here that relates the 15-degree angle with the side opposite that angle, and we want to know the side that is adjacent to that angle. That sounds like a problem for tangent. So tangent of 15 degrees is equal to 170 over x. And this is a caution. The previous examples that we've done related to this, our variable was always in the numerator, and now it's in the denominator. And a lot of my students will get in the habit of just taking whatever side length they have times the trig function of the angle, and they won't think about where values are placed within the ratio. In this case, I would think about multiplying both sides by x. So I have x times the tangent of 15 is equal to 170. So x is equal to 170 divided by the tangent of 15 degrees. And when I calculate that out, I should get a value. Let's head over here to the calculator. So 170 divided by tangent. I want to make sure that we are in the correct mode, which we are. Tangent of 15. 634 feet. So we got that value at approximately 634 feet. Is that reasonable? Well, the 15 degrees goes with the side length of 170. 75 degrees, this should definitely be a longer side, and it is. So 634 feet is the distance from the boat to the base of the cliff. And that concludes our lesson on right triangle trigs, using it to solve applications in the real world.